Wave power. You need to know of the operation of an oscillating water column, OWC, which is an ocean wave energy converter. Also, we need to go through the derivation of the equation which tells us the power per unit length of a wavefront, assuming a rectangular profile for the wave. So what is wave power? There are a number of ways of using wave power to produce electrical energy. This is what's called a limpet. It's a land-installed marine-powered energy transformer, which is basically what we're going to be looking at. The limpet device uses what's called an oscillating water column to generate a maximum of 500 kilowatts of electricity. So, how does the wave power work? Or in particular, an oscillating water column. Now, as the wave comes in, you have a chamber of air here, and the only way that water can come in is through this way, underneath the wall to this chamber. So as the wave comes in, the water is pushed up, and it will force air to go through the turbine. So this air is forced through the turbine is connected to the generator, and the generator generates electricity. And then when it goes back, the air goes in the reverse direction, and there again it is able to generate electricity. We have to determine the power per unit length of a wavefront, assuming it's a rectangular wave, and the power given is half rho g a squared v. A is the amplitude of the wave. So the power per unit length of a wavefront. We're assuming that it's a rectangular wave, so if you have a cross-sectional area, A by A, the area is going to be A squared. Rho is density, G is gravitational constant, V is the velocity of wave. The way this is done is that there's a mass of water which is moving up and down, and this change in gravitational potential energy is what provides the energy. So the power per unit length is half A squared rho GV, and we need to derive that now. What is the volume of water in the red area? Well, it's going to be this height times by this times by the length. So it's going to be A, the amplitude, times by lambda over 2 times by the length of the wave. We know also that the mass is equal to the volume times by the density. So find the loss of the gravitational potential energy of the wave. It's going to be mgh. It's going to be m, which is the mass. The mass is this volume that we've calculated here, times by the density, times by g, times by h. This is the mass that we've just calculated here, volume times density. So it's A times by lambda over 2 times by L times by rho times by G times by H, where this height here is the change in height of the body of water. And how many waves do we get arriving per second? We know that V is equal to F lambda, so the frequency is equal to V divided by lambda. So it's going to be this amount of kinetic energy. So the power is the total loss of GPE, gravitational potential energy, per second. So it's going to be A times rho lambda over 2 times by L times by rho times by G times by A. This A multiplies by this A, so we get A squared, and then multiplied by V divided by lambda. We have lambda here, and we divided by lambda, so they cancel. So the power per unit length is half A squared rho GV. In the past paper they have asked this to be derived.